Hi, today I'm going to demonstrate how to use external libraries such as NumPy, SciPy, Matlab, XLRD or Python PPTX with ANSYS ACT. Usually these external libraries are developed for C Python application. However, ANSYS ACT is based on IronPython. There are many flavors of Python. The standard Python is known as C Python. One of the flavor which is basically a Python code which is working on .NET framework is called IronPython. So ANSYS ACT is developed based on IronPython. So all the external libraries which are compatible with C Python not necessarily be compatible with IronPython, and in turn not necessarily going to work with ANSYS ACT. As of today, NumPy, SciPy are not compatible with ANSYS ACT. So here I am going to demonstrate from ACT, which is basically nothing but IronPython, how to call C Python using subprocess module, which in turn will call NumPy, SciPy or XLRD to do some data manipulation. To demonstrate this, I'm going to use two examples. In example 1, we have certain portion of our FE model. Let's assume this hole. This hole is circular in shape initially. This is distorted due to some loading acting on it. Okay. Now what I'm going to demonstrate, read the UX displacement of this hole which is computed by ANSYS. Write the UX displacement vector against the node number into a CSV file. Then read that CSV file inside C Python. Then scale that vector by some displacement factor which is a user input using NumPy. Then write out the manipulated UX vector into another CSV file. Then read the manipulated CSV file inside ACT and plot it. Okay. The another example I am going to show here is that because of the loading, the hole is distorted. Now we want to represent the distortion of the hole in a polar graph, which is nice. Okay. I'm going to explain this concept using these two examples. To do this whole exercise, there are certain prerequisites. First, we need to install the standard C Python. You can install any version of standard C Python that is compatible for the external library that you are planning to use. So I have downloaded Python version 3.7.2 from this website and installed. Next, we need to install the required external libraries through the Windows command prompt. Here is the typical procedure to install NumPy. Python -m pip install NumPy. Upon the installation, we can ensure the successful installation. Same way we can install SciPy, Matplotlib or whatever external libraries that you need to install. I'm leaving this process to your expertise because you may want to use different libraries that is available in the market. So once the libraries are installed, please make sure you could import those libraries and you can execute some namespaces of that library. Say for example, simplest thing to check is the version of those libraries that you have installed. Okay, let's go with the example. So I'm bringing up, this is my setup. This is a small plate meshed with shell elements. Both the ends are fixed. Both the ends are fixed like this, and there is a moment load applied here. Because of this moment load, the plate is getting deformed and the whole circularity is get distorted. Okay, so our interest is to study the distortion of the circularity of the hole. For that, we can see the directional deformation in whatever direction we want. Our objective is to scale this directional deformation by 10 times. Okay, first example. So I'm just going to insert the new ACT button, which is going to ask to select scope to the geometry which I want to process. I'm selecting these two edges. I want to scale this by 10 times. Okay, so this is the factor. If we just evaluate in the background, it is going to call CPython, as you can see, then process the data and give us the results back. This is the directional deformation without any scaling. This is the directional deformation with 10 times scaling. Okay, so for example, if we change the scaling to 5 times, it's going to scale 5 times. In the background, it is going to call CPython and process the data using NumPy and plot it back. This is a one example. The another example I wanted to show is that we could get this information as a chart. This is basically calling the 4 objects. First one is the radius of this hole, which is 10 mm. Then, okay, let's look at this each object. This is nothing but the radial displacement in local coordinate system, and this is nothing but the equivalent stress around this hole. And there is a radius. The radius of this circular hole is 10 mm. This is extracted using a user defined result. Location X means the theta R direction in local cylindrical coordinate system. Okay, this is constant, and theta is nothing but location Y again in the cylindrical coordinate system. This is the theta in radians unit. Okay, this is going to give 360 degree or 2 pi in the stuff. Now I have gathered all this data. This is the length of this circular hole. This is the change in radius. This is original radius. This is theta in radians. This is the sigma xx along this hole. Now what I want to plot is the original circular 10 mm radius and the distortion. I'm going to demonstrate it through another ACT. Once we select this chart object and click this another ACT button, this is going to call CPython in the background and plot the information like a circular hole with 10 mm radius. Then the amount of distortion is very small, in the order of e power minus 5 mm. In order to show in a readable scale, I converted this mm into a micrometer so that both are in the similar scale, 10 micrometer range or maximum 15 micrometer range. But this the circular hole is 10 mm diameter. Okay, I will just now show you the procedures involved. First, I will explain about this this ACT, which is about scaling it. So first one is to develop the button that we are seeing here. Basically, this is having 3 user inputs. One is the displacement scale factor, and geometry selection is to scope to the geometry, then the scale factor. Then we are going to write out the information for Python in some file, and also after manipulating the data in NumPy, we are going to write out in some other file. Okay, the input and output name. Okay, that's what we are defining here. This is going to call first the Python script main3. The main3 is like this. So on click it is going to create the custom results. So custom results is nothing but this object it's going to create. So once we say evaluate, it is going to call a function called manipulate. Okay, so this manipulate, what we are trying to do is we are trying to first get what is the working directory of this project and what is the user file directory. Okay, user file directory is nothing but if you say open solver directory, and if you go 3 steps back we will see user file directory. I will delete all the files that exist here. So we are getting the user file directory path, and then we are going to, excuse me, we are going to give some name for the input and manipulated result file. The input file name is automatically taken as the extension name plus disp ux inp, but you can give any name here. Okay, you can bring in your own logic. Then we are creating the full path by combining the directory, user directory and the file name. Okay, then we are going to write out. To write out, I am opening a file, this input file, which will open in the user directory. Then this collector ID is going to contain all the nodes in the 2 scoped lines. For all these lines, I am writing out the node ID and the displacement, UX displacement value into the CSV file. Then I am going to get the scale factor value. So whatever the user is providing as a input here, that value is fetched inside this ACT code. Then I am going to fill these 2 fields, okay, with the input and output file name. Then we are going to call a function called call CPython. This function is defined here. This CPython function is the important part here. So what we are going to do is Python has a standard capability that's called subprocess module. Okay, with this subprocess module we can open any exe program along with certain arguments. Say for example, if I want to, this is the exe of the program that I want to open. So I'm going to open the standard CPython exe that is installed. Then the 0th argument supposed to be the input file that this exe is supposed to use. Okay, so what I'm going to do, I'm going to supply another Python file which will get executed by within this CPython, and also we are going to pass some arguments for this CPython execution file. Let's look at what is this NumPy func3 look like. Okay, what is this going to look like is, it is going to have a function. First I'm going to define a function. This function requires 4 arguments. One is the user file directory, input file, output file name and the scale factor. Then remember that this file will run inside CPython. Okay, then it's going to import a NumPy library and a Matplotlib library. Then this scale factor whatever is supplied is coming here as a scale factor. Okay, now again I repeat, the important part here is the subprocess. Again this subprocess is not actually owned by ANSYS. This is the standard capability of the Python or the CPython module. You can explore more about the subprocess capabilities in open internet resources. Google search about Python and CPython, understand subprocess. So there are many ways. popen is one way, call is one way. There are many ways to call that functions. So again I will explain here. This subprocess call or subprocess popen will have things like that. It's going to take one single list as a input for this popen. This list can contain many number of elements. Okay. Another important thing is all the elements in this list must be a string. It cannot transfer any list or an integer or a float. All the elements of this single list must be a string. The first field is always the exe. This is a 0th. This is, you can imagine this field as a list. This is 0 index, 1 index, 2, 3, 4 like that. Okay. So the first argument is the input file. Then these are all the arguments. Okay. Now when we are calling this, we are going to pass. First we define a function like this. We are not actually executing the function inside CPython. We are just defining it. Okay. We are going to call this function inside CPython through this. So for this it requires 1, 2, 3, 4 inputs. I'm just getting the 4 inputs. Okay. These 4 inputs are coming from here. This is 0. I don't want to pass this because it's always a fixed file. Then the user file is nothing but the first argument, and input file is second argument, output file is the third argument, and the scale factor value is the fourth argument. Remember that all the elements must be a string, cannot be an integer or float. So this scale factor, though it is a float number, I must convert that as a string to pass to this. So once I get this here as a string, again I need to convert this as a float. Okay. So by this way we have passed all the information from ANSYS to CPython. Now this CPython is going to get all this input and it's going to open the input file and read the lines, convert that as a 2 columns and close the file. Then it is going to convert the node number list as an array, and also it is going to convert the second column, which is nothing but the ux vector, as an array and multiply by the scale factor. Finally it is going to save this node number unscaled ux into a output text file. Okay, that is nothing but the output text file name is given here. Okay, this is the file it's going to give. So by this way it is written out the output file. If you come back here after calling this CPython, what is going to happen is it is going to use CSV module. Then it is going to open this output file and read the node number versus scaled ux column. Then once it read that value, then it is going to plot set values. This is nothing but the node number versus the scaled ux value, that is going to plot as a result back in mechanical GUI. That is what is happening. Okay. Now let me explain, run this code. Let's look at the user directory. Now there is nothing. When I clear this and generate this, evaluate this result, it's going to call Python in the background. And the user file, you could see 2 input file and output file created. Okay. So this will contain node number versus the unscaled displacement, and the output will contain node number versus the scale displacement. Okay. Remember that how to use any external libraries are really up to your expertise. I'm not going to discuss anything with how to multiply or how to manipulate as such, and also it is not really part of the actual ANSYS SciPy tool. Okay, so I leave that with you. Now let me explain the second example of plotting a polar chart using Matplotlib library. For this we are going to plot the angle versus distortion of the circularity in the hole. So we are going to plot 2 data. One is the initial perfect circle radius, which is 10 mm. Then the another one is the distortion plot. The distortion is very small, in the order of e power -4 -5 mm. To bring in similar scale, the distortion is plotted with respect to the undeformed circle in micrometer dimension, whereas the whole radius is plotted in meter dimension. To do this, the first thing is we need to develop a XML file to bring in a ACT toolbar. So this is the XML file. So here there is no load or result object created. As soon as we click this button, it is going to bring up the graph. Okay, it is not going to insert any item in the tree, any object in the tree. Let's look at how to do this. So the first thing we need to do is that we need to gather all the data that we need for plotting in one object. Okay, here the chart object. So to plot the polar chart, we need two information. One is the angular position of the nodes. The second one is the radius of this hole, and the third one is the radial displacement in cylindrical coordinate system. Okay, so this result object shows the radial deformation of the hole in a cylindrical coordinate system, and using the user object, the location x in cylindrical coordinate system gives the radius of the hole, and the location y, the theta, is given in the cylindrical coordinate system. We have this information. And also say for some reason if you want to plot the stress distribution around this theta of this hole, then we could do that. So now I have collected all these data like radius, change in radius, stress values, all in this single graph. Okay, now our objective is to first we need to bring all this data into a list. To do that, this XML file is having two Python script. One is main.py. The main.py looks like this. First we are going to create a list, empty list. Then we are going to collect all the data in the table. For that, there is no official API to collect the data in data table pane. So here is the unofficial procedure to get the data in any data table into list. So this TC actually refers to this data table. Once we point to this data table, we can count how many rows and how many columns are there in this table. Then we can start collecting this data. All this data is referred as a text for this particular cell. Okay, so now I am counting how many rows are there. Then I am going to gather data. This is list ordering. So here cell corresponds to the each cell. So here it starts from row number 1, 2. Okay, we need to start collecting from row number 2, and this is column 1. Column 1 corresponds to serial number. Let's say theta is in column 6, 1, 2, 3, 4, 5, 6. We are collecting theta. Likewise, we are collecting radius, change in radius, and stress. Stress is in 1, 2, 3, 4. Fourth column. We are collecting this. Now the list is populated. Then we are collecting the user directory. We are going to use this user directory to save the plot. Then we are identifying the installation directory of this ACT. Then we are providing the path for CPython.exe. Then we are going to supply the input file that should be run inside CPython. Then we are going to call the subprocess. As I explained earlier, this subprocess is the standard functionality of IronPython and CPython. This is not specific to ANSYS as your CAE tool. There are a lot of capabilities with this subprocess namespace. In the last example, we have seen an example of using subprocess popen. Okay, now we are going to use the another feature called subprocess call. Again, it is going to take one argument list. This will take only one list. As I explained, all the elements in the list must be a string. But here in this case, we have to pass theta, radius, change in radius, all as a list. So if we want to pass this to CPython, we need to convert these lists as a string. Then back in the CPython program, we need to decode these strings as a list. So now we have collected all this information, but when we click this execute Python, when we click the button, it is going to call a function called execute CPython. execute CPython is looking like this. Basically, the input is none is the requirement for a subprocess callback. So what we are going to pause here is that inside this function we are going to call this whole function, okay, which really collects the tabular data and going to pass that as an argument to the CPython. So this function is going to pass the CPython input file to the call CPython function. So the input file for CPython is placed inside the installation directory. Okay, that path is given here. Now let's look at what the CPython file is going to do. CPython file is looking like this. So there is a function defined. Then we will call this function. Okay. So now what this function is going to do is that it is going to take 1, 2, 3, 4, 5 inputs. These 5 inputs are nothing but the 5 inputs that we are passing from here. So this is 1, 2, 3, 4 and 5. Okay. So the first one is user files, that's the user file directory. Then theta, radius, change in radius and the stress. So now here we are going to call this function by passing these 5 arguments. These 5 arguments are system arguments like this. As I explained earlier, the first field is always the exe file and argument 0 is the Python file that's supposed to be called. Then this is argument 1, 2, 3, 4, 5 like that. Okay. So the argument 1 here actually corresponds to theta. Okay. Here as we are passing this theta, this is passed as a structure. The list is converted as a string. That string need to be decoded as a list and again need to be converted as a float. That's done here for theta, for radius, for change in radius, then for stress. Okay. Then we are going to use the standard functionality of Matplotlib library to plot a polar chart, and here we are going to plot 2 data. First one is theta, then we are going to plot radius, okay, and we are giving some label. Now remember that the radius is in mm. Now we want to plot change in radius as a micrometer. So what we are going to do is that we are going to convert the change in radius as a NumPy array. Then we are multiplying by 1000 to convert millimeter to micrometer. Okay. So here we are using the NumPy functionality and the plot is done using Matplotlib functionality. And we are giving title, we are controlling the number of major and minor axes and things like that. These are all standard Matplotlib functionality. This is the standard NumPy functionality. I'm not going to discuss more about NumPy or Matplotlib capabilities or functionality as such. Okay. Then we can save. This is going to show the plot, and we can also save the file inside our user directory. Okay. Now this gives the whole functionality. Now let's try to run the whole thing. One important point in the whole thing is that this table data collection is always going to point to the table data that is currently active. If we want to collect this table, first it is important to highlight this table and collect the data. Say for example, if we highlight this table and trying to run this macro, it will try to collect the data from this particular table. But this is not having 6th column and all, so we are going to get some kind of error. So it is important that we highlight the object that is compatible with the code that we have written. Okay, then we click this button. So what it is going to do is it is going to collect the data and plot. For troubleshooting purpose, we could use the print functionality here, like print the message from CPython, and we are printing the user file directory. This is variable 1_2. This is the theta values and all plotted. Okay, so basically here what we are doing is that, see, if you are using standard CPython with NumPy or Matplotlib library, if you want to draw a polar chart, we will pass some x variable and pass some y variable, we plot it. Okay, here what is different in using standard NumPy and Matplotlib in conjunction with ANSYS ACT is that instead of we passing this variable manually, we are getting this x and y variable from ACT. That is the only difference. The important is that you have to make sure this function as it is runs in standalone CPython. Otherwise, we are going to get some error. So this gives the plot until we close this chart box. This Python command window is active. Once we close this, CPython get closed and it will continue to process rest of the commands written in main.py. Okay, this is the feature we have used in previous example. We used CPython to write out the CSV output file. Then after that, it's going to, after this writing out the file, it is going to read the CSV file and do rest of the things. This is the way we can use CPython in combination with ACT. Right now, this code is always bringing up the chart GUI like this. Suppose if you want to run this entire script in a batch mode so that you don't want the GUI to pop up, what we could do is that we could say, instead of let me delete all these files. Instead of we showing the graph in a separate graph panel, we could just request save the image in the user directory. Say for example, let me refresh the ACT. So usually you are going to get some error messages. The error message that you see here are related to the integration between the ICT and Python, nothing to do with the coding issue in these Python files. Okay, but you have to go through these error messages. If there are any syntax error or tab intent error, that you have to correct it. Okay, let me clear this. Now if I run this function, you see here there is no files here. If we run this, it is going to execute Python in the background, but it is just going to put the plot. Let me just open with this. Oops, yeah, okay, this way you can use that. Later you can use these plots for your report or whatever purpose. Okay, I hope this gives you an idea about it. Let's say when I just forgot to mention one particular point, it may be better to explain with this example. Okay, let's go back to this NumPy. This file which we are going to run inside, this is for the example of scaling the data. In this one, what we are going to do is that this whole file is running inside CPython. This has nothing to do with ANSYS ACT as such. So we need to make sure this code is really error free. Okay, and moreover, though we are printing something, first of all, we are not holding the CPython display. Let's look at this. As I am executing this code, let me make this as a plot display like this. Here I will show my unscaled deformation. Here I want to show my scaled deformation. Let me run this script. So it is executing CPython, but it just closed. We cannot really see what is there. If you want to really hold that CPython display for some troubleshooting, we can print some information and all. What we could do is that we could use some dummy graph. say for example here, I'm just going to plot some dummy data here. So this is going to bring up the new graph GUI. Until I close that graph, the Python window is be on hold. Okay, let's look at this again. I'm refreshing. Let me clear this and evaluate this again. Now it's going to plot this data, something whatever we have plotted. This is just a dummy, we are not going to use it for any purpose, but the Python window is still visible. We can print our user file path, we can print whatever it is. Say if you want to print the scaled one, we can print. So we can use this for some kind of a debugging purpose. Okay? I also want to explain about another way of debugging. Now we have this code which is going to generate the scale displacement like this. We can use Python output to debug certain purposes. Let's say we are generating that. But when we are writing the code for CPython, if there are any errors, let me introduce an error here. Instead of NP, I will put NP1. Now this is going to make this code not to generate the output file, and hence it cannot mechanically cannot plot the graph. For that purpose, to demonstrate this, let me go and delete all the inputs that we have generated. I'm going to refresh my ACT. Now this is going to give some errors, but this is not going to give the error related to that NP1 change. Okay? These are all related to Python and ACT integration. Let me delete all these things. Let me also clear the generated data. Now, because of the error that is present in the code that is meant for CPython, now I don't expect this to generate the graph from CPython, and also it will not generate the scaled displacement results. But if you look at the error message, it says there is an error in main3 line number 56. If you go to main3 line number 56, so it's not giving any clue. The actual clue is here why it is not running. Okay, so if you have any such problem, the good way to troubleshoot is that, as I mentioned earlier, we need to make sure this function which is meant for CPython is having no errors. How can we check this? We can open standalone Python IDE, whatever IDE you use. I use normally the Python shell that comes with standard Python. We can use this function. Okay, we are just going to define this function. I'm just going to just say print function defined but need to be called. Okay, I'm just running this. So if I run this stuff, so okay, now the function is defined, but we need to call that. Okay, to call this function, we have 3 arguments to be passed: user files, input files, and output files. But when we were running this, it should have generated the input file. That part is taken care by the ACT. But the issue has happened while processing that input file. Okay? So now we know what is the user file directory for this one, what is the input file name, and what is the output file name. So instead of we using these system arguments, now we can manually use the user file directory and input file name and output file name. The another one is the scale factor. I'm just going to use this string. I'm just going to call by manually passing those arguments. The moment we execute, we can see here the error is related with line number 34 of this function. Okay, so this is related with NP1 not defined. So if you look at this, we can easily catch this error. This is another way of debugging the code that is going to run inside CPython. Okay, so once we understand where the error is, we can quickly come and correct this error. Save the file, refresh the ACT, clear the data, evaluate. Now everything is going to run smooth. Okay, this is another way of making sure the Python file which we are calling inside CPython is error free. I hope this gives you some idea about how to interface ANSYS ACT with CPython and call standard libraries. I created this video for the users who are already familiar with using CPython, external libraries in CPython, and also they have some familiarity in building basic apps inside ACT. Okay? This is really not meant for somebody is first time start learning ACT. For those, I would recommend start looking at ANSYS basic training courses. So in this whole process, what is very important thing is that calling subprocess. Okay, the subprocess part is very important thing to interface ANSYS ACT with CPython, which in turn call any external libraries. As I mentioned earlier, this subprocess is the standard functionality of the CPython. Of course, there are certain functionality of the standard CPython is available in IronPython as well. This is not specifically developed by ANSYS, so we can get a lot of literature and documentation about the subprocess module in IronPython or standard Python textbooks. ANSYS uses IronPython version 2.7. You can go and check here what version of IronPython is being used in the ANSYS Workbench version that you are using. I know that the subprocess is a module, as I said. We can check the location of the subprocess file like this. We can import OS, and once we import the OS and the subprocess modules, then we can get the path of the subprocess.py file. Okay, this is really responsible for the subprocess.popen or subprocess.call. I know that there has been updates in this subprocess.py that you can get from internet. If some functionality is missing in the version of IronPython that ANSYS is implemented, you may use the latest subprocess.py file and try to replace this location. But you make sure when you are replacing, you are taking the backup copy of this folder. If something goes wrong, we can restore the original functionality of ANSYS ACT. I hope this gives some idea about how to interface ANSYS with any external program which can be called using exe and by supplying the input file. Okay, this is not limited to CPython. Say for example, if you are using Anaconda for your C compilation, so what we need to do is, instead of calling the CPython exe, we need to call Anaconda exe location, and we need to supply input file which Anaconda can process. As simple as that. And it could be any other external program. It may be your own internal code or interfacing with some other software. So this functionality really opens up new world of possibilities to interface ANSYS with other softwares. Once you familiarize this concept, I hope you can develop more complicated application that is needed for your organization to automate certain process or develop some tools which you can deploy across larger audiences, or you can supply to your clients. Thank you very much. Bye.